We're going to talk now about the normal distribution. The normal distribution is important. It arises as an empirical distribution that people would see again and again when they measured biological aspects. And there's a famous French mathematician named Quetelet who thought that the distribution that you see normally occur around an average was essential for the process of natural selection and for evolution. And Quetelet had this great quote: if any individual possesses all the qualities of the average, they would represent all that is great, good, and beautiful. It's a little different than the way we think about the world today. If I told you this is what I tell my kids before they go to bed: hey, tomorrow, just be average, just be right in the middle, you'd say, hey, why don't you aim a little bit higher? But trying to aspire to be right in the middle was an interesting idea. Now, the normal distribution we're going to see takes a very special shape and has special properties that will allow us to do a lot in statistics. In order to draw a normal distribution, we have to plug in two parameters. We're going to see this word again and again. A parameter is something that describes a population. This is easy to remember. P is for parameter, P is for population. We're going to use Greek letters whenever we're talking about parameters. So in this formula, which you don't need to memorize, you don't even really need to understand it, but you need to notice there's some Greek letters that are in here. The first is this one. This is the Greek letter mu. Mu starts with, sounds like M. That's the same as mean. So this is easy to remember. Mu, mean, and that is going to be the measure of central tendency. Where is the average of the population? The other thing that's important to draw a normal distribution is this here, this little sigma. Sigma S standard deviation, also easy to remember. So we have to plug in a mean and a standard deviation, and then we will get a normal distribution. Most people think that there is one normal distribution or the normal distribution, but there's actually an infinite number of them. How many different means can you think of? 10, 12, 1,000, 15, 1.5. There's an infinite number of means. There's an infinite number of standard deviations. And when you plug in a mean and a standard deviation, you get a different normal curve. It might look like this. It might look like this, depending what those parameters are. Oh, I want to show you this applet. So there are some cool applets online where you can actually play around and make different normal distributions. So here is one. You see that Greek letter mu equals 100. That's our mean. That's the center of the curve. Sigma equals 10. So that's our spread. And if you look down at the curve, we saw an example like that with the bone mineral density, where if you're a 90, you're below the mean, but you're not that far below the mean. Now, if we change this standard deviation to, say, 2, notice how my mean is in the same spot, but now when I look at the spread, where's 90? 90 is way, way down there. So I've changed the parameter of this distribution. I can change the mean itself. Here I'll plug in mu equals 1,000. Sigma is still 2, so that standard deviation or the spread is 2. And here you can see what the normal distribution looks like for a mean of 1,000 and a standard deviation of 2. Let's say we increase the standard deviation here to, say, 100. Now there's a mean of 1,000. Standard deviation is 100. And applets like this have another cool feature, and it's something that's special about the normal distribution, is you can reference or locate an individual point in that distribution. So if you look at that curve, you see that number 1,200? If I said to you, what percent of the points are above 1,200? Or how weird is 1,200? You say, well, most people are below 1,200, but there's some percent that's higher than 1,200. And we can put that in here in this blue box and watch what happens in the red box when I hit enter. It's going to be something around, I don't know, take a guess, 1%, 5%, about 2%. And we're going to use this feature of the normal distribution, this ability to reference individual points in this distribution. We will use this again and again. So here are some examples of normal distributions. When I change the mean, the curve just slides to the left and to the right. When I change the standard deviation, it gets wider or narrower. But why study the normal distribution so much? There are some characteristics of it that are very important. The mean, the median, and the mode are all equal. The distribution looks the same to the left and to the right. So if you know what's going on in one tab, on one side, you know what's going on the other side. We're going to say that the tails never touch the axis. And so you can reference any point and say what percentage of other points are to the left or to the right of this. Now, in this class, there's really only a couple things you need to memorize. One of them is the definition of the p-value, and the other one is this. In a normal distribution, we say that 68% of the points are within one standard deviation of the curve, of the mean. What English word would you use to describe 68%? Maybe most. Most of the points are within one standard deviation. If you go out to two standard deviations, almost all, 95% of the points are within two standard deviations. And if you go to three, this will be that blue that you see in the curve right here. If you go to three, within three, we would say 99%, which is not all, but it's like people would say literally almost all, or like seriously, almost all of the points are within three standard deviations. So these are important, and we're going to use these next when we talk about z-scores and about referencing individual points in a distribution. So you will memorize this.